In this video, we're going to take a look at bond enthalpies. And so a bond enthalpy is the enthalpy change when 1 mole of covalent bonds in the gaseous state are broken under standard conditions. So a couple things to keep in mind is that bond breaking will require energy, so they are endothermic. So the delta H will be a positive value. Whereas when we're making bonds, it's going to release energy, so that's exothermic or a negative value. So bond enthalpies are really important to kind of keep in mind that they are only used for reactions occurring in the gaseous state. They can be a bit inaccurate because they don't take into account intermolecular forces. So it's important to kind of keep that in mind as you're working with these different values. So an example might be, for example, if we take hydrogen gas and we break that HH bond into 2 hydrogen atoms, then the bond enthalpy for that is plus 436 kilojoules per mole. Always a positive value because it takes energy to break the bonds. Another example might be HCl. And if we break that covalent bond into a hydrogen atom and a chlorine atom, then that delta H is around roughly the same. It's around 431 kilojoules per mole. So that's just to give you an idea of a couple of different bond enthalpies. Now, there are tables of values of average bond enthalpies. We're going to talk about the average part momentarily. But just taking a look at our table here. So this first one here is for single bonds. And so the way you kind of read this is you would look for the bond you wanted. So say you wanted a carbon bond with a hydrogen, and you would come down and look for the intersection, and then that value is 414 kilojoules per mole. Remember, bond enthalpies are defined in terms of breaking bonds, so they're always going to have positive values in these data sort of tables. Multiple bonds are over here, so you can see a double bond, triple bond. They all sort of have very different values. Really important to keep in mind that these are averages. So what do I mean by average values, and why is this important to know? Well, the average bond enthalpy in terms of a definition is the same as the definition of bond enthalpy, except the average refers to the fact that the bond enthalpy is different in different molecules. And so the value quoted is the average amount of energy required to break a particular bond in a range of molecules. So the way that they get these values is they will take a whole bunch of different molecules, different types of molecules, and look at breaking, say, for example, the CH bond. And then they would take an average of all of those bond enthalpies over all of those different molecules in order to come up with the value that is in that particular data table. So they're not super accurate, and they can be quite off because they're taking into account a variety of different molecules. Now, that being said, you can calculate the delta H of a reaction using bond enthalpies. And the way you would do that is you would take the sum of all the bonds broken, the enthalpies of all the bonds broken, minus the sum of all the bonds that are formed. So if we were taking a reaction for our reactants to our products, and we wanted to find the delta H of reaction here, we'd have to take our indirect root, and we would be looking at reactants to gaseous atoms. So this is all of the delta H's of our bonds that are broken. And then we would take our gaseous atoms, our products to our gaseous atoms, so we would be subtracting the delta H's of all of the bonds that are formed. And that will give us our direct root of our delta H of reaction here. So essentially, it is a Hess's law kind of problem again, just with making and breaking bonds now instead of some of the other examples that we've seen. So let's look at an example. How would we figure out the enthalpy change of a reaction given bond enthalpies? Well, we've got a reaction here of ethene reacting with bromine to make our 1,2-dibromoethane. So kind of a nice strategy here is to actually draw out the structures, because then you can see what bonds are being formed and what bonds are being broken. So I'm just going to draw them all out here. And here is our final product. We got 2 CBr bonds. We got H's here. And that's it. Okay. Now, the way I kind of like to tally this up is I'll look at all the bonds that are broken and kind of list them on one side, and then all the bonds that are formed on the other side. So looking at bonds that are broken here, we're breaking a C-C double bond. We're breaking 4 carbon-hydrogen bonds. And then we're breaking 1 bromine-bromine bond. So if we look up those values in our data tables, you can pause and kind of work this out for yourself if you want. But we've got 614, this one's 4 times 414, and 193. And then I'm just going to tally all of those up, and that gives us 2463. If we look at the other side now and look at bonds being formed, we're forming a CC bond here. We're forming 1, 2, 3, 4 carbon-hydrogen bonds. And we're forming 1, 2 carbon-bromine bonds. So carbon-carbon bond is 346. This is again 4 times 414. This one's 2 times 285. So if we added all of those up together, we get 2572. Now we can do our delta H of reaction from here. And remember, we're taking the sum of the bonds broken, which is 2463, minus the sum of the bonds formed, so minus 2572. And that gives us negative 109 kilojoules per mole. Okay. This works because everything's in a gaseous state, so we can use bond enthalpies here. If one of those was in a different state other than a gas, it doesn't really make a lot of sense to use bond enthalpies. So that's how we can use bond enthalpies to figure out the enthalpy change of a reaction. That's it for this video. We'll see you in the next one.